Hey there, it's Shannon Myers, and today we'll be looking at trails, paths, and circuits as they relate to discrete math. So this next definition is a page long. It has several components to it, and the premise for it is that we let G be a graph and V and W are vertices in G. A walk from V to W is a finite alternating sequence of adjacent vertices and edges. Of the graph G. Thus, a walk has the form in general of V0, E1, V1, E2, all the way down to V sub n minus 1, En, and Vn, where the V's represent vertices and the E's represent edges. V0 is equal to V and Vn is equal to W, and for all I equal to 1, 2, all the way down to N, and then some Vi minus 1, and Vi are the endpoints of EI. All right, so that's the very general setup. The trivial walk from V to V consists of the single vertex V. So it turns out, if you have a trivial walk, you do not have to have an edge to have a walk. All right? Okay, so next up, a trail. So these definitions build on each other. So make sure that you learn them all and learn how to relate them to each other. Okay, a trail from V to W is a walk from V to W that does not a repeated edge, right? Next up, a path. So a path from V to W is a trail that does not contain a repeated vertex, right? A closed walk is a walk that starts and ends at the same vertex and now we get to circuits, okay? So a circuit is a closed walk that contains at least one edge and does not contain a repeated edge. A simple circuit is a circuit that does not have any other repeated vertex except for the first and last. Okay? Because remember, since a circuit is defined as a closed walk, that first and last vertex will always be there. But for a simple circuit, those will be the only ones that repeat. Okay? Because the first will be the last. All right. I'm sure you get that. So here we go. Here's sort of a table to help guide you. All right. So these are characteristics across the top row and the types of graphs along the first column. So for a walk, can you have a repeated edge? Yep, You can. So we'll just say allowed a repeated vertex. And the reason I don't say yes is because it doesn't have to have a repeated edge. Okay, so it's allowed but not required. Right? In a walk can have a repeated vertex, right? A walk can start and end at the same point, same vertex. And does a walk have to contain at least one edge? Good. No, because why? A simple walk does not have an edge. All right, so let's look at a trail. Can you have a repeated edge on a trail? No. All right. A repeated vertex. You can. Right? The main thing for our trail was that you can't have a repeated edge. All right? It's a walk without a repeated edge. So it can start and it could end at the same point. And if it's a trail that is a simple walk, right, then it wouldn't have an edge. So it doesn't have to have at least one edge. Okay, so for a path, if you look back at the definition for a path from V to W is a trail that does not contain a repeated vertex, right? And so here with the path, you have to have, no repeated edge because it's a trail, right? And it just said you cannot have a repeated vertex. And since you can't have a repeated vertex, you can't start and end at the same point. But I suppose in the, real simple case where remember a graph could contain just a single vertex without an edge. So you don't have to have an edge for the path, okay? All right, so closed walk. Right, so remember, circuits and simple circuits are defined from closed walks. So in a closed walk, you can have a repeated edge. You can have a repeated vertex. You have to start and end at the same point. All right, so the same vertex. And again, you do not have to have an edge. So a circuit is a closed walk that has no repeated edges. So you can't have a repeated edge. You will have a repeated vertex. You have to allow that because it starts and ends at the same point. So this is a yes as well. And with this one, you have to have at least one edge. So a simple circuit means that it's a circuit that has no repeated vertices except for that first and last. So you will not have your repeated edge. This one, first and last only. Starts and ends at the same point, yes, and it has to have at least one edge. Cool? Okay, so here we go. Here's a graph I drew up. I think it's from one of the examples in your text. All right, so hopefully it's clear enough. But in this graph, I've asked several questions, and we want to determine whether the following walks are trails, paths, closed walks, circuits, simple circuits, or just walks. Okay, so here we go. I actually redid this where you've got the graph for each part of the problem, and that way you can trace each one. So here we go. Let's check out this one. And I'll go ahead and do this, I guess, in highlight color. Okay, so we've got V1, E2, V2. So V1 is where it starts, okay? E2 V2, and then where does it go? So I've done these 3, and then now we're going to be going V2, E3, V3. So here we go. So you get the idea, right, on here. And then continuing, we're going to have V3, where we just ended, E4, V4. And then we'll have E5, or V4, E5, V2. So notice what has happened. We have a repeated vertex right here. So V2 repeats. Okay, just something to take note of. And so where were we? We just did V4, E5, V2. So now V2, E2, V1. So V2, E2, V1, right? So E2 repeats. And then we are now at V1, E1, V0. Okay, so did we start and end at the same point? No, right? We've got repeated edges, we've got repeated vertices, so here, what do you think it's going to be? It can't be a trail, right? So anything with a repeated edge, it can't be, right? So the only possibilities, if you look at it, are a walk or a closed walk. But did it start and end at the same point? No. So this is just a walk. So good so far? All right. So now let's go down to our next one, which is just the vertices. Okay, just the vertices. And so the vertex set, and that's okay. All right, that will lead you where you need to go. If you want to, you can write it where it's more specialized. I mean, this is really equivalent to, the edge that joins them. And so which edge joins V2 and V3? Good, E3. So this is equivalent to saying V2, E3, V3. So that's the first two. Then between V3 and V4, what do we have? E4. So we would have E4, V4. And you don't have to do this, but this can tell you if you don't want to look at the graph and you just want to look at vertices and edges, what type of graph it is, if it's a walk or something more specialized. In between V4 and V5, we've got edge 6. And in between V5 and V2, we have edge 7. Cool so far? So one thing I wanted to point out is that we do start and end at the same vertex. If you see here, we start and end at V2. So let's just, trace what we have and go from there. So what do we have? We've got V2 goes to V3. So you can look at it however you want. Whichever version of the graph you want to look at. And then we went down here to V4 from V3. And then from V4, we went to V5. So actually, I should have drawn it really going this way. You'll learn about directed graphs. And then from V5, we went back to V2. And so notice that we did not repeat an edge. We started it and ended at the same endpoint. So what do you think this one might be? And by the way, the reason I was able to write the graph this way while you're thinking about this is because there were not, these two graphs are equivalent, okay? Equivalent sense there aren't any parallel edges, just to be clear. Okay. You can't always just do that. If there's a parallel edge, you have to make sure you're representing everything. Okay, so here we go. Looking at our chart, we start and we end at the same spot. So we know for sure we have a closed walk, right? We have no repeated edges, right? We do have an edge, so we definitely have a circuit. And the only circuits that repeated were the first and the last, right? So therefore, we have a simple circuit. So this is a simple circuit. So do you see what we just did there, though? We knew that it was a closed walk. So once we knew it was a closed walk, we knew that it was either a circuit or a simple circuit. All right. Okay, so on this one, let's just go ahead and trace what we have and go from there. So V4 going to V2, and then we can write in what we've got going on as we go. So V4 going to V2 gives us what? V4, E5, V2. V4, E5, V2. Okay. And then coming back here, so remember we started at V4, right? And look, we're going to end at V4. So it's definitely going to be a closed walk. All right, so next up, we're going from V2 to V3. So V2 to V3 goes like this. And so coming back here, what did we do? We went V2, E3, V3. And then going next, we went from V3 to V4. Okay, so V4 is going to repeat not only first and last, do you see, but within the closed walk. So we're going to have a repeated vertex other than first and last. So just keep that in mind. So we went V3, E4, V4. And now where are we going? We're going from V4 to V5. So that one happened to be V4, E6, V5. And the next step is from V5 to V2. And so we have V5, E7, V2. And then our last one goes from V2 to V4. So to get from V2 to V4, we repeat an edge. Do you see that? I'll go kind of over. We repeat, we repeat edge 5, okay, to get from V2 to V4. So this is something that has repeated circuits, or sorry, not repeated circuits. V4 is it starts and ends at V4, right? But V4 is also in the middle, so it can't be a simple circuit. And then we've also got repeated edges. So if you take a look at which one was the one that repeated? Edge 5, right? Edge 5 repeated. So when we come here, our repeated edges allowed only in a closed walk, since we knew we had a closed walk. And so it's not a circuit or a simple circuit. This is a closed walk. Cool, cool? And by the way, you don't have to show all this work. If you can eyeball it and see, you know, what I'm talking about, then feel free to do that. I just want to make sure you understand. Okay, so this next one, I'm just going to draw it out and then note what happened at the, you know, as we go. So V2, it starts and ends at V2, right? So let's just note that to ourselves. And so going in order, we go from V2 to V1. And then we go from V1 to V5. We go from V5 to V2. So V2's also in the middle, right? So we're going to have more than just first and last repeating. So that knocks out simple circuit. All right, and then from V2 to V3 takes us here. And then from V3 to V4 goes down here. And from V4 back to V2. So what we have going on is, whoops. It looks like there's no repeated edges, right, that we came across. But there's a repeated vertex, V2, that is more than just first and last. So this guy is going to be a circuit. Cool, cool? All right. Now, let's see what we have for this one. So it doesn't start and end on the same vertex. So what do you think about this? We know it's not going to be a circuit or a simple circuit or a closed walk. So now we just need to think about, what is this going to be? Just a regular walk, a trail, or a path? So coming back, let's do it. So it starts at V0, right? And it goes V0 to V5, V5 to V2, V2 to V3, V3 to V4, V4 back to V2. So do you see that V2 repeats, that vertex repeats? And then V2 to V1. So we didn't have, sorry, that was a little shaky here. We did not have any repeated edges, but we have a repeated vertex, right? So V2 repeats. So what does that give us in our chart? Well, check it out. It's going to be, we said we had no repeated edges, but we had repeated vertex. So to me, it looks like it's a trail, right? Can't be a path because of that repeated vertex, right? But it can be a trail. So a little more specialized than just a walk, but it's definitely not a circuit. Cool, cool? All right, so then this last guy here, let's do it. It doesn't start and end at the same vertex, right? So we're kind of in a similar situation. So V5 is where we start. And when we head over to V4, and from V4 we go to V2. From V2 we go to V1. So notice that we have no repeating edges and we have no repeating vertices. So I'm thinking this is going to be a, dun, 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 you got it, a path. All right? So hopefully this exercise, I know it took a while for this example, but hopefully this exercise helps you visualize that and helps you remember what these are. Okay, so our next definition, let G be a graph. Two vertices, V and W, of G are connected if and only if there is a walk from V to W. The graph G is connected if and only if given any two vertices, V and W and G, there is a walk from V to W. So this can be a little tricky. So I'll show you. So symbolically, G is connected if and only if for all vertices V and W that belong to the vertex set in G, there exists a walk from V to W. Cool, cool? All right, so here is a lemma. Let G be a graph. If G is connected, then any two distinct vertices of G can be connected by a path. If vertices V and W are part of a circuit in G and one edge is removed from the circuit, then there still exists a trail from V to W in G. If G is connected and G contains a circuit, then an edge of the circuit can be removed without disconnecting G. So for you electrical engineers out there, these are some important principles. Okay, so we'll go into another definition and then an example. So a graph H is a connected component of a graph G if and only if H is a subgraph of G, H is connected, and no connected subgraph of G has H as a subgraph and contains vertices or edges that are not in H. Okay, so I really like this one. All right, so in example 2, let's use this graph below to answer the following questions, right? Is this graph connected? And we want to find all the connected components of the graph below. So one part of it is really obvious, right? This F, vertex F, G, right? That part of it, can you see it's not connected, right? So we can easily answer, it's not connected to the rest of the graph, right? But it's still part of that graph. So kind of like, in algebra, piecewise functions, they're not always connected, right? And a lot of different graphs are not connected. So here we know that part's not connected. But you know what? There's another part that's not connected that's a little bit harder to see. Can you tell me what that is? Beautiful. The path AB DE is also not connected to this other one here, which we can say goes from C to C. There's different ways you could draw this. I mean, different ways you could name this graph. But anyway, long story short is that these graphs, these parts of the graphs, they're not connected, the different colors. So let's talk about the different connected components. So the first one that we outlined in the purple, right, was what, C, I, H, and then there's some repeating of edges going on there, and J to get them all covered. And then number 2 we can look at was F to G. It doesn't matter which order you do them in. And then number 3 was this A, B, D, E portion. The whole graph is the whole graph, right? What you saw initially. And then what we just did where we drew the parts of the graph that were connected. Cool. All right. So, and that's it for this lesson. So, I hope you have a wonderful morning, afternoon, or evening whenever you're watching the show. And if you like what I'm doing, please subscribe. Bye.